Hey everyone, and welcome to The Explainer. Today, we're going to crack open a classic coding puzzle that's all about finding patterns in what looks like chaos, grouping anagrams. It's a really cool problem that shows off a surprisingly elegant way of thinking. Okay, let's just dive right in. So to get started, just take a look at these three words on the screen. Eat, tea, and ate. I mean, they look different, right? But what's the real connection between them? You probably see it right away. They're all made of the exact same letters, just shuffled around. And yep, that's exactly what an anagram is, a word that you can form just by rearranging the letters of another word. So our challenge isn't just spotting one or two of these, it's figuring out how to teach a computer to find and group all of them in a huge list of words, totally on its own. So, how in the world do we do that? How do we get a program to understand that eat and tea are basically family? Well, the entire solution hangs on one simple but honestly brilliant insight. It's a little sorting trick that completely unlocks this whole problem. Let's just walk through it together. First, we take the word eat. If we break it down into its letters, E, A, and T, and then just sort those letters alphabetically, we end up with a new string, 8. Pretty simple, right? Okay, now for the fun part. What happens if we do the exact same thing to one of its anagrams, like T? We break it down to T, E, A, sort them, and look at that. We get the exact same result, AET. And that is the big aha moment. And this right here is the heart of the solution. It doesn't matter how jumbled the letters are. If two words are anagrams, once you sort their characters alphabetically, they become identical. This sorted version, that's our magic key. So this is the really crucial idea. That sorted string, AET, in our little example, it acts like a unique fingerprint for that whole group of anagrams. It's what we call a standardized or canonical representation. Any word out there that sorts down to AET belongs in the same club. Okay, now that we've got this awesome insight, let's build our first solution around it. We'll just call this approach sort and group because, well, that's literally what we're about to do. Now, to pull this off efficiently, we're going to use a data structure called a HashMap. The easiest way to think about it is like a digital filing cabinet. Each drawer has a unique label, that's our sorted fingerprint, and inside each drawer, we're going to keep a list of all the original words that match it. So here's how the process works, step by step. We loop through our big list of words. For each word we find, let's say 8, we generate its sorted key, which is AET. Then we go to our HashMap, find the drawer labeled AET, and we just toss the original word, 8, into the list inside. We just keep doing that for every single word. And once we've gone through every single word in our input list, our HashMap has done all the heavy lifting for us. It'll have all these different lists, one for each group of anagrams, all perfectly organized by their sorted key. And just like that, problem solved. Now, that first solution, it works perfectly. It's solid. But, in the world of programming, we're always asking, can we do better? Can we make it faster? And that brings us to a slightly different and often more efficient approach, the count and key method. This really gets you thinking, is sorting the letters of every single word really the absolute fastest way to create that unique fingerprint? I mean, if you have some really long words, sorting might start to take a little bit of time. Is there a more direct way to get there? And the answer is yes. Instead of actually rearranging all the letters, we can just count them. Think about it. The one thing all anagrams share is that they have the exact same characters with the exact same frequencies. 1A, 1E, 1T. So here's how we can build a key this way. Let's take our word T. We can create a little array with 26 slots, one for each letter of the alphabet. Then we just go through the word and tally up the counts. We've got 1A, 1E, and 1T. Then we can build a key string from those counts, maybe using a hash symbol to separate them. And guess what? This string also works as a perfect, unique fingerprint. All right, so now we have two really solid strategies, one that sorts and one that counts. Let's put them side by side for a second and see how they really stack up, especially when we start thinking about performance. Okay, this table really tells the story. For the sort and group method, the time complexity is O of m times k log k, where m is how many strings we have and k is how long they are. But now look at count and key. It's just O of m times k. It's missing that log k part. So why is the counting method faster? Well, it's because just counting the characters in a word is what we call a linear operation. We basically just pass through the letters one time. Sorting, on the other hand, is just inherently a more complex task. And that little log k factor represents that extra work. So for really long words, the counting method is definitely going to win the race. Okay, before we wrap this up, let's just quickly touch on a few important little details that make a solution truly complete. And then we'll lock in the big idea you should really take away from all this. A truly great algorithm has to handle all the weird stuff, what we call edge cases, like what if the input list is totally empty? Or what if it has empty strings in it or duplicate words? A really robust solution using either of the methods we talked about will handle all of this stuff gracefully without breaking a sweat. But look, if there is one thing to remember from this entire explainer, it is this: the power of creating a canonical representation. That's the big idea here. It's about taking something that seems messy and complicated, like a bunch of jumbled anagrams, and figuring out a way to create one single standardized format, that fingerprint, that represents the whole group. And that's the final thought I really want to leave you with. This whole fingerprinting trick is incredibly powerful, and it's not just for words. So the question is, where else could you use this idea? Where else could you create a unique key to find patterns and bring some order to messy, seemingly unrelated data? It's something to think about.